Chef at the moment.
This is about relativity, and my relativity is based on a different understanding of particle physics, and it is, I can say at the beginning, also not related to Einstein, but I will explain it why related to Lorentz. And we need to rethink areas of physics, in my understanding, and the reason is that we have many problems in physics, and we'll call it the crisis of physics. And the arguments are we have all these problems which are unresolved in present days. Nobody, maybe with Higgs, but we'll talk about this extra, but nobody has solutions for all these things, really. And we could have solutions if we change our understanding of some basic things of physics, which are traditional, but have no good arguments in my understanding. So, the paradigm, which I think is a cause for the problems, is, in the sense of Thomas Kuhn, the opinion elementary particles are point-like and don't have an internal structure. Relativity is caused by the properties of space-time. And in my understanding, this is completely the wrong way. The right way would be to say elementary particles are extended and they do have an internal structure, and relativity is caused by the properties of fields. And the internal structure is this internal structure of elementary particles. Okay, the context of my talk will apply this on special relativity, on particle physics, which includes the origin of mass and general relativity. Let's start with special relativity. Relativity with Einstein is based on assumptions about space and time, as we know. The question is this the only possible way, and is it a good way? I say no, it is not. We will show the other way, the Lorentzian way to relativity is the right one, as it is based on conventional physics, so it is simple in contrast to Einstein. It is free of the paradoxes which are typical for Einstein's relativity, and it refers to physics, not to structure, so it makes us understand other areas of physics. It has this side effect. Okay, the elements of special relativity, as we know, are contraction, dilation, the main things, and as a consequence, the constancy of speed of light, the increase of mass, and this Einstein energy-mass relation. So, history of contraction is an old one. Heaviside has found that electric fields must contract at motion. This comes from Maxwell's theory. Fitzgerald and Lorentz have used this knowledge, this understanding, to explain the null result of the Morley experiment, because if fields contract at motion, also objects contract at motion, so also the apparatus of Morley contracts at motion, and that is the reason that one cannot see any effect there. And it contracts, that was found by Heaviside by this, what we call later the Lorentz factor. This was explanation for Morley was also accepted by Einstein, but it was an ad hoc explanation, so like trial and error, a mathematical trick. That is wrong. I think Einstein did not know about Heaviside, which was typical for Einstein. And this relation is said was proven to be true for all kinds of fields. So it's a general true rule. So dilation, this is the next point. Dilation also has some history. Ziegler was the first one to say there is some motion in the smallest object, that means now in elementary particles, at the speed of light, and this was okay, we have got further information about this by Louis de Broglie, by Dirac, and Schrödinger has evaluated the Dirac function of the electron and found that there must be an internal motion here at speed of light, and he called this Zitterbewegung, which means some trembling motion. He felt not comfortable about it, but from the equation it's clear that it is there. And if we accept this, that there is something with the speed of light in the particles, then this is a general cause for dilation. We can see it as this little simple example. If we have this light clock, light bulbs going forth and back, used as a clock, and we move this light clock, then the path is now extended in this way, in the motion, and the dilation, so the extension of the path, is described by Pythagoras. It's very simple, and again we see that the Lorentz factor is in fact Pythagoras. And this is the general explanation why we have dilation. We can apply this, and will this apply this to a particle model? This is not a particle model, but this is one, and I will explain this in detail, because this explains dilation and many things aside of that. So we assume that elementary particles are built by two subparticles. which orbit each other at the speed of light. They do not have any mass individually. These subparticles, which are called basic particles. And the properties of this model are given by all these people we know, by the buoyant frequency, by Dirac-Schrödinger, or what I've shown, speed of light. There must be two particles to follow the law, or not to violate the law of momentum. They have to orbit because they have a spin and a magnetic moment that can only be done by one orbital motion. And the mass of the subparticles, the basic particles, must be zero to make possible that they move at c. That follows from relativity. And this model now is called the basic particle model. It has to have a name and is in no conflict with the experiments, which is sometimes said, and I will explain this later more in detail. So dilation now applied to our particle. Here we have our particle again. Particle model, and now we think it moves into axial direction. And now the circular motion turns into a helical motion, and on the helical motion, one circuit is longer and takes more time. And it's again Pythagoras to say what the extension of this period is. We come to the same Lorentz factor. It's quite simple. Now we can write it in this way as the derivative of the proper time, of the internal time of the system, and we can say this Lorentz factor describes the speed of the internal time, the speed of the proper time. And now we can use this for an easy imagination. We can square it, then we come to this, and we can reorder it, and we have a very simple understanding. We can take our elementary particle as a clock. The clock has an internal speed, that is the proper time in the clock, and it has an external speed, and always the vector sum of the internal speed and the external speed is the speed of light. I think that it's easy to have a direct understanding of this. So, this is important to describe the temporal properties of an elementary particle. We have to keep this in mind because this will be a good starting point for general relativity. So this now is something which is funny. Contraction is by this Lorentz factor, dilation also, it's the same. So it's very tempting for a mathematician like Minkowski to say we build a four-dimensional space out of both because they follow the same rule. But this is mathematics. It's very elegant, but that does not reflect a physical situation. So to accept this, to accept Minkowski, to me, it is a sellout of a physical understanding of relativity. And we will follow here a physical understanding of relativity in contrast to this. So this was special relativity. Now we'll later come to some aspects in the context of particle physics, that means increased mass and so on. We have to understand what the origin of mass is and have to understand our particle model. So we have these, two subparticles orbiting. They are bound to each other, but they keep a distance. The only way to do this, we cannot use a planetary model because they do not have any mass. The only way to do this is to have a multipole field, as it is given here. The blue particle has, at this side, a potential form like this, shape like this, and the red one this, and every particle resides in the minimum of the potential of the other particle. So that keeps them apart at a certain distance. And this is not very new in physics because if you look how we look to the bind of some atoms in a molecule, it's exactly it is a similar multipole bind, as you know it as sigma bind or what it is called, P bind. It works in a similar way, but there it works with electric force, and here, I said the first time, it is the strong force. And this shape is described by this equation. This was the simplest equation I could find to describe such a shape of field, and it works fantastically, so it seems to be the good one. Again, the binding force here is a strong force. That's a bit unfamiliar, but it can be proven that this must be true. So what we know, we'll go to the next one, it's the same in general. They are bound to each other, to say it again, and keep this distance. That means if you press them to make them closer to each other, there's a force pulling them out to the original position. Or if you want to draw them apart, there's another force pulling them to the original position. Yeah? But now, if you take one particle, move it away, the other one will follow. It keeps this distance. That's very clear, I think. Yeah? But another thing is also clear. This field only propagates at the speed of light. So it will take some time, if you move this particle, that the other particle notices this motion and will follow with a delay. And this delay is given here. You see, shown here in a little bit. The blue particle is moved now to this point. The field of the blue particle had followed. Here it's not yet followed because this is the limitation of the finiteness of the speed of light. And here we need a force to take the blue particle out of the minimum. So we need a force, but only for a short time, because after some time, the field of the blue will follow, the red particle will follow, the field of the red particle will follow, and again the blue particle is in the potential minimum. And that means we need an intermediate force to change the motion state of this configuration. And an intermediate force to change motion state means inertia. That is the cause of inertia. And that is very simple and fundamental to say why we have inertia in our world. And that works not only as a model, but also quantitatively very correctly. So, this again is our equation for this field. And now, when we apply a constant acceleration to the particle, to the system, to the blue particle in my case, the red particle will follow with an offset caused by the finiteness of the speed of light. And this offset causes the force, and this force is given by this equation, and we can also write this is the acceleration, can write it this way, and here we have the unknown parameters, integration constant for the directions, and this field constant, and we use here, here we have to clarify that we use here the well-known relations, which we know from Planck and from Einstein. We can also derive these equations from this particle model, so it is consistent in this way. And if we apply this, we end up for this formula for the mass of an elementary particle. And you see it's very simple. It has only the radius of the particle as a variable, all the rest is fixed, and it's assumed that this is universal for all elementary particles. Now, if you doubt that such a simple model can explain all particles, it can be true for all particles. With particles here I mean fermions. That it's true for all fermions, then we have a very simple and good check for a charged lepton, for instance, like the electron, but it works for anything else or others. We can use this classical equation for the magnetic moment, and we know for electrons and all for the other leptons for measurements what the magnetic moment is to determine the radius. Then we take this radius, insert it here, and we get the correct mass for this particle. That works for all leptons from experiments, and it works also for all quarks. There we have to use some results from quantum mechanics, but they have the same result. Now we can combine both, and we come to eliminate the radius, and we come to this equation, which you know for the electron in this Bohr magneton. And interesting in this case, and this is that you find in all textbooks the statement that Bohr magneton can only be derived using quantum mechanics, never classically. I have done it classically using this particle model, and I think this is a good indication that in this case we wouldn't need quantum mechanics if we use the correct model, a good model, yeah, the correct one. Now, increase of mass, this is again our equation. Now, we know that we have contraction, so at motion, the radius will contract by the Lorentz factor, so the mass must increase by the Lorentz factor. That is increase of mass. Very simple. Look how Einstein did it. Very complicated. This is simple. Now we can do the next step. If we put an object in motion, we have this increase of mass. We have kinetic energy, increase of the kinetic energy. So if we put both in relation to each other, we end up with this equation. It's very simple again. 5 lines of equations. And look how Einstein did it, very complicated, a very complicated thought process of Einstein. This is extremely simple. And it's physically, it's based on physics, not on some funny ideas, abstract ideas. Now, spin, we can reorder this equation. Then we get this here, this is a classical definition of angular momentum, and we see it as constant. We know it is half not h bar, but that has to do that we have here at a certain moment a certain component which causes the angular momentum which can be measured. So all this can be used. So now, mainstream physics tell us, scattering from electrons show us that the electron has no internal structure and is point-like. Why do they say this? This is a misunderstanding if we use this particle model. These experiments are done in the way that, for instance, a proton with high energy is bombed onto an electron, and they say if the electron would have subparticles at some energy, the electron should be decomposed. But if we assume that the subparticles do not have any mass, it can never be decomposed, because you can accelerate this basic particle at arbitrary acceleration. The other one, as it has no mass, can follow without any delay and without any force which is applied. So this argument, the normal argument, is not mainstream physics is not applicable here. And now, if there are these scattering experiments which tell us that the electron is very, very small, they tell us that the basic particle is very, very small, because that makes the scattering here. That's quite similar to the Rutherford experiment. Rutherford wanted to show the size of the gold atom, but he didn't find the size of the gold atom, but of the nucleus. Here we do not find the size of the electron, but the size of the basic particle. And that is all consistent. So the arguments of mainstream physics do not apply in this case. So now we know about the magnetic moment. It's not exactly the Bohr magneton, which was here, but which has a correction which is a Landé factor. And this correction was found by a theory developed by Julian Schwinger. And he invented vacuum polarization to explain this, and got the Nobel Prize for it. And this correction factor is this one. But now we can have also to do a correction in our particle model, because when I derived this, I used only the strong interaction within the electron to derive this. But the electron has also electric charges which I have neglected in that moment, and they have to take into account, and these electric charges make a correction factor, and the correction factor is, look, this one. The same equation, the same number, without vacuum polarization and any other quantum mechanics contribution. This is another example where we can, we may not use quantum mechanics, we can live without quantum mechanics to explain something. Okay, this is again the model of the electron in standard physics, mainstream physics. They say, how can an electron with this point-like have magnetic moment and spin? They say there's a cloud of virtual particles invented by Feynman, and this cloud explains why we have these properties like magnetic moment. If we have this particle model, we do not need virtual particles. From the previous, we've also seen vacuum polarization is not needed in this case. So, we don't need it. Here it is simple, and we do not need, that's also a consequence, renormalization. We do not need strings, because these things have been invented to overcome singularities, or to live with singularities which come from which occur in the normal physics, mainstream physics. If we have this model, we do not have singularities, so all this is not necessary. So now, cause of mass. We have now, at the situation, is two models for mass. One is the basic particle model, as I've shown you, and the Higgs mechanism. So what is about Higgs? There was a boson found in last July, presented at LHC, and they have seen something, this boson in these channels, or not seen it. And the first two are very clear. This is photon-photon channel, clean signal, but too high by 2.5 sigma, too high, higher than expected. This is ZZ, clean and plausible, has a good significance. With WW also a good signal, but with little significance. But tau was nothing seen with not too much significance, and bottom also nothing with lower significance. But if we take this together, we can see with a probability of around 8% or so, it conforms to the standard model. With 92%, it conflicts with the standard model. This will further be investigated. Okay, that's the present state.
There are more up-to-date results than those. There are more up-to-date results than those.
This is the most up-to-date.
No, it's not.
Are connected.
There's more up-to-date than those. The first three are all 5 sigma results now. And
no, whiskey is with it. The WW is not. We have seen it in it. I have a picture of it.
But I work with these people. They're my colleagues.
Yeah.
I see them every day. The first 3 are above 5 sigma.
Yeah.
And the last one has been claimed for 3 sigma.
This one?
Yeah, BB.
Okay, I haven't seen this. This is the state, and we have magnitude that controls physiology, also the sign is wrong. That is something which is completely out of order. So there's another thing. How can we calculate the masses? Here, this is the equation from the Higgs theory, which for the mass, for instance, of the electron here is we have a V, which is a general field constant, which was adapted. But here, this is the coupling of the electron, but there's no theory which tells us what is the value of this, so we do not have any independent result from this equation, and we cannot say anything about the accuracy. It's very much completely undefined. If we take a basic particle model, we have this equation I've shown you. We can use here the electron radius of the electron, and the result here, the accuracy is almost 10 to the minus 6. So if you say here is no accuracy, here is a high accuracy, you see what the quality of these particles is, in my opinion. That is a great difference, not in favor of things. Okay, this was particle physics. I have to, how much? Any two? Okay, now next will be general relativity, and this also Lorentzian, not following Einstein. Without Einstein, without space-time, and I will show you how this works. What is gravity? My statement, gravity is nothing else than the change of the speed of light in the vicinity of an object. I must say in combination with this particle model, otherwise it could not work, but then it works. And this is this equation, perhaps you know it, about the change of speed of light in the gravitational field. So all phenomena, that's my statement of gravity, that means all phenomena of general relativity are caused by this change of the speed of light. We do not need anything more except the particle model. And this will now be demonstrated. So we start with the Shapiro experiment. We know it is radar ranging from the Earth to the Venus, and from the time needed for the signal we can determine the distance between Earth and Venus. Now if we repeat this experiment in a situation where the signal passes very closely to the surface of the Sun, to the Sun in general, then we get an extension of this time, and we can use this also to determine the reduction of the speed of light, and Shapiro has confirmed that by this experiment, that this equation of the reduction of speed is true. So Einstein says, okay, the space has changed, and this is different understanding. Now we can look to this situation. We have the Sun, and we can build concentric circuits, no, not circuits, but spheres around the Sun, and on each surface we have a constant speed of light. Outside, a higher speed of light, inside, a lower speed of light. And what happens now if we put a particle going, let a particle go through, for instance, light going through this situation? It is reflected. That is very classical physics. And the reflection angle can be, the reflection parameters can be determined by building essentially the derivative of this equation, and what we get out there. I can show the calculation is classically defined as the website. Here, for the vertex, we get this acceleration towards the Sun, and you see already this is Newton. Now, if we calculate this deflection angle, we get from this calculation again this famous result of 1.75 arc seconds. This was, in that time, the big breakthrough for Einstein, because in 1919, only Einstein has predicted this angle in the correct way, or others have said either nothing or a wrong angle, and so everyone said Einstein with this concept of space-time must be correct, because he's the only one who gives the correct result. No one has, by that time, used reflection. The reflection process, later it was done by Roman Sexel and others, and it shows that the reflection process exactly gives us the same result like Einstein's space-time. Not only numerically, but also analytically, it is exactly the same result. So also here we do not need space-time. So now this was acceleration for fastening object. Now we have acceleration for an object at rest. This here is our our elementary particle without and circling, orbiting without an gravitational field. Now we switch off the gravitational field. Now this part is reflected downwards and we get an accelerated motion towards the gravitational source. And it's, for your imagination, it's a similar thing that the particle passing the sun but now wound up in this way. And the result here, if we calculate again, it's the acceleration at the surface, we find again this is Newton. So we have derived here the Newton's law of gravity in this simple way. And what we can say, that this acceleration is independent of the diameter of this particle, so independent of the mass of the particle, because the mass is reflected by the diameter, as we have seen. So we know why this acceleration downwards has no dependence on the mass, and there is no need for an equivalence principle. We do not need a principle. We have the result here in a direct way. Sorry, I need a little bit. So these have been the simple examples. Now we come to the more theoretical part. The treatment of general relativity, we have to do it in a more general way. So we have here these very known proofs of general relativity, which are always taken as proofs for Einstein's theory, but we can show it that we can prove them as well with this model, which I call the lensing wave. Here, this Shapiro and gravitational lensing I've just shown. Geodesic effect and stilling also, I am not showing it here, but it can be, also this time can be deduced from this model. Black hole also a deduction of speed of light, it's not much more. Perihelion advance is normally explained by the Schwarzschild solution, so all the other things are generally explained by the Schwarzschild solution. So I will come to this now with more detail. This is a common or a usual way to write it down in 2 dimensions, that is enough in this case. And we will now show how to deduce this equation, and it is not complicated. Oh, what happened then? Yeah. Okay. Here we start again with this temporal behavior of an elementary particle at motion. This is without gravity. Now we split this speed because we have to turn to polar coordinates. Now we switch on the gravitational field. That means we have to apply these equations. I've shown you this for the speed of light, and the change of field extension also follows directly from this. Okay, it's just a statement here, but easy to show it. So we apply this to this equation, to this simple equation, and this already is the Schwarzschild solution. Now we multiply by this factor both sides to get a more familiar view of it, and this is the Schwarzschild solution. That was very simple actually. Now, if you look to a textbook of general relativity, you will learn how this is done using Einstein's theory. And this is this way. I've copied this from a popular textbook, and this more than 80 equations you have to go through, but that's not the bad thing. But here, to understand this, you have to understand the Riemannian geometry of a curved 4-dimensional space for a curved 4-dimensional space. And you know, everyone knows that this is not many physicists are able to do this. And here you need Einstein's field equations, which is also not very easy, also some challenging task. But if you are very intelligent and you like to work hard and do all this, you get the merit at the end and you end up with the Schwarzschild solution. Okay? Or you do it this way, that's so easy, you can teach it at school. And it's not only easy, simple, it is based on physics and not about on ideas about structural ideas about space-time. So some people tell us, and that is normally told in university lessons, that Einstein has found the simplest way to solve relativity problems in his way of space-time. Look, this is Einstein's simple way, and this is the way without Einstein. So perhaps we should rethink this thing. And I have done this want to convince you. Gravity, we have seen gravity is the change of the speed of light in the vicinity of an object. Now the next question, what is the physical reason for the change of light in the vicinity of an object? So, the question, why is the speed of light reduced? And there's a simple model where we can see how it can work. It will work. This is this light object moving here. Now, in free space. Now we have here two elementary particles in the way I've explained them. And here we have the forces which keep both particles to each other, to bind them to each other. And these forces are here shown as exchange particles, and the exchange particles, of course, do not go from one particle to the other, but are everywhere in space, and they interact with this particle, and they have attracting parts and repelling parts, and so they make here cause to be a random zigzag motion of this light-like particle. And at the end, in the result, the average speed of such a particle is reduced. And we can now use this model to calculate how big the reduction is. And the result of this calculation is this equation, which I have shown you now many times. And what we can see and what follows from this particle model. Okay. So the problem of quantum gravity is solved in this way. Okay. So we have open problems in cosmology, quantum gravity, just mentioned. Dark matter problem, that means the rotation of rotating galaxies is too great. They should be composed, they don't do it. This is given here by the rotation curve, this is the rotation speed, that is the distance from the center of the galaxy. And what would be classically acceptable by Newton or also by Einstein was such a development of a run of speed, dependency on speed. And what we observe, there's much higher speed, rotation speed, here like this measurement point. The difference, the conflict is this black line. But now if we say gravity has nothing to do with mass, we can use the photons, we have a lot of photons in the gravity, and they give us this contribution. And this is almost ideal to explain this. Also neutrinos would do it, but the density of neutrinos is insufficient, but the density of photons is sufficient to explain this. And if we look for the particles like axions and neutralinos, which are taken now as the candidates for dark matter, they would have this shape here, not this shape. It can only be done by photons and neutrinos, not by these particles. And the recent result of this Xenon 100 experiment, where they have looked for such particles, they didn't find anything. So we are lost in this photon. The photons are the solution. So now, dark energy, also a big late topic these days. We know that we have the idea of inflation to explain the horizon problem. It was also in previous talks explained. I won't repeat it. But to solve this problem, this causal connection between different areas of the universe, one has assumed that in the beginning the space was very, very small and then extended rapidly, and then at the end now it's extending by a slow rate until these days. We can also, as an alternative, assume that the speed of light was very high in the beginning, went down rapidly, and now the speed of light is going down smoothly. And these both possibilities, answers are completely equivalent. So there is, if we do this, we have also the explanation for the causal connection. So, what's dark energy? Dark energy was found that experiments of Giese and so on were explained here. Here we have the supernovae which are used for it. These are the new ones, these are the old ones, and the old ones are too slow compared to the new ones to move here from the Hubble line. And so it was said, it's interpreted in the way that the new ones are accelerated. But now, if we take this picture, that we say the speed of light now in our period is reduced very slowly, smoothly, but it is reduced, then we can use it. You know, the speed of the supernova is determined using the Doppler effect, and in the Doppler effect equation, the speed of light. So if for the old supernova we assume that there was the speed of light higher, we get a higher speed for the old supernova, and then move to this side. They are again on the Hubble on the Hubble line, so there is no acceleration and no need for any dark energy. The problem would be immediately solved. Even with Einstein's ideas, that's nothing I would say here, we can solve, can have this kind of explanation. So, problems with...
I need to come to a conclusion.
Yeah. Einstein's equivalence of Einstein's gravity and acceleration is not true because the charged particle sense there is a difference between gravity and acceleration. Ether is not necessarily, as we know, for linear motion, but it is necessary for rotation. So we need an ether in some way. So I would like to, at the end, say something, mention something of the philosopher Leitner who promoted Einstein. He has made a very good comparison. He said Einstein's relativity has a logical connection to equivalence to the problematic system. Lorentz relativity has a connection or logical equivalence to the Copernican system. So what do we have one is the problematic system and the Copernican system. Also the philosopher Popper has made thoughts about it, why Einstein didn't like the ether. It was also not a physical reason, but he found out that more this view of the world. So these are our summary. Why not space-time? Special relativity can be founded on physics. Paradoxes are avoided. General relativity is founded on physics. It's easy. Open problems are solved and so on. Why not point-like particles? With expanded particles, we can understand in the classical way. We can either understand relativity. We can understand magnetic moment, constant speed of spin in the classical way. We do not need virtual particles to a certain extent. Perhaps we do not need them at all. We do not need renormalization and no strings in the cases I
I think we have to move on now. Thank you very much for that.
On my counter.
Well, okay, but I've counted 40.
Not being unfair.
No, we had some discussion before we started.
No, but that was your choice, not ours. I think I have to go on to the next speaker. I don't think we've got time for questions. Okay, thank you anyway. Let's just do that provocative thing. It'll be time to talk about it afterwards. Okay. Yeah. The next speaker is Miles Osmond, and he's going to give us 2 talks. The first one for 40 minutes and the second one for 30. And so what's the time?
So while this is being fired up, can I just say, we have a saying, the proof of pudding is in the eating. And it's the product that matters. Does it suit everyone who eats it? If the main ingredients are right, the details of how the cook does it can follow later. So, although the cook is what we start more or less with, it's the product which is important to follow. So, I'm going to show you how I think I can implement natural ether with the primary requirements of natural ether. And the other things will follow, and they are what really makes you think the first part should be taken seriously. The physical mechanism of gravitation setting the scene. The idea that gravitation might be some large-scale vortex effect, but in an ether of unknown quantity seems to have been originated by Kepler and was soon followed by Descartes and Newton. But Newton didn't pursue it as far as the origin was concerned. But from the early 1860s, the particulate nature of matter being well established by then, others started thinking in terms of individual particles. They began with molecules, the smallest objects known to them. These individual particles having a vortical character, and they stopped by vortex rings a lot, of ether in motion as the source of our mutual attraction and mass property. And here, 150 years later, I'll be building on those endeavours. And in 1865 sorry, that's 1978, it's 1878, I'm sorry, that's a misprint, came Maxwell's famous equations based on the findings of Gauss, Faraday, and Ampere. From these, he established the properties in ether essential to the existence of and propagation of electromagnetic waves. These are continuous math functions with no suggestion that the ether could have a particulate nature, although again, such as even in visiting from the particle scale. He did have a go at trying to make the ether particulate, but gave it up. The crucial and apparently contradictory requirement which I address here and implement, even uniquely perhaps, is that the ether must combine quasi-superfluid behaviour with elasticity and shear. And the final item in our scene is that J.J. Thomson's work on cathode rays led people to identify the electron as the carrier of electric charge, thus regarding negative charge to be particulate nature, not to be found in any other guise. Yet, here I will reason that on the contrary, the vast majority of negative charge in the universe exists in a distributed form, with electrons incorporating only a tiny fraction of it. And to the really starting point for what I'm going to talk about is that I have two major quarrels with the current form of relativity theory. The first one is embracing the function of transverse electromagnetic waves as perfect messengers between frames, but denying the presence of Maxwell's equation ether, essential for existence. It's like saying, I want the ripples, but I can't be bothered with the water. And that's a failure of plain, straightforward logic. This enabled Einstein to avoid any possibility of transmission effects associated with ether, and to postulate that C was an absolute constant of physics. And I think that physically unrealistic in a real universe. But it was in fact my observation and recognition of one of those transmission effects, which I'm referring to in my second talk, in 1959, which started me right from the start on the present trail. Now the second absurdity is promoting, despite contrary and growing contrary evidence, the physical absurdity central to GR equations that fundamental particles, as Albrecht was also saying, that are infinitesimal singularities. This would require that their external physical properties, mass, magnetic moment, either be developed within zero volume by inventing a new law of intrinsic properties for zero volume, or treated as intrinsic to that particular infinitesimal space. Why that bit different from that is, sorry. The consequence for fundamental physics has been very severe. In any electromagnetic theory, communication of force between two electromagnetically defined objects is, if they are finite size, progressively velocity limited to being zero at c, as Albrecht was also pointing out. So this is what we observe with electromagnetic accelerators, not mass increase, reduction of pushing efficiency, if you like. The extra mass that emerges has been created from the enveloping ether, also accelerated, see later. And this opens our door to the design of a particle interior to give each chosen an unchanging mass, regardless of whether you or I are moving fast or relative to it or not. Now, continuum theory as a rewarding replacement for relativity theory contains two main features. Implementing Maxwell's equations as massless, all-pervasive, compressible, quasi-superfluid continuum of a negative electric charge. It is not a carrier of electric charge. Electric charge is its very nature, so it's massless. And it's compressible, constrained by the self-repulsion of its charge, and it's quasi-superfluid, not perfectly superfluid, because shearing motions of charge are subject to Ampere's law, and this provides magnetic energy storage and effective elasticity in shear needs to support the existence and propagation of transverse electromagnetic waves. And the second leg of the process is following Maxwell and all these other people in making finite-sized particles out of it as vortical constructs of ether motion. And this will lead us in two important directions. One, the physical mechanism of gravitation, which is what this first talk is about, and the second one is the particle-associated random motion of the ether, and that's what the second talk is about. So, that's right. Constructing particles out of ether, quantifying the ether. This is something which is really a very important step. The ether can be only one sort of charge, and I've actually said it's going to be a negative charge, but that's for independent reasons which I can't go into, what we see at the start. How do we get particles of opposite charge? Combine electrons and positrons with opposite relative charge. This is relative charge, remember. We suppose one to contain more ether and the other to contain less. The layout of this diagram really means to say that the charge density in the core of the positron tells you what the mean density of the ether is, if you think in those terms. On this basis, the mean charge density of the ether, you can get the charge density in the positron from that result, and its known relative charge, which is 1.6 times 10 to the minus 19 of a coulomb, the charge density must be at least that, which is a fantastically large. This huge charge density means it gives it self-repulsion and immense force potential. If it is locally displaced, and I'll show that it's done so by gravitation, may well provide the rotational reference frame from which all directional devices depend. Now, our directional devices have two kinds of property. The rotational gyro and the Foucault pendulum are both dependent on inertia or gravitation, whereas the laser ring gyro is dependent on the Sagnac effect, which is electromagnetic propagation. And they all have a steady reference in direction. Now, this is where we get into how the cook made it, as it were, rather than the final ingredients. And consequently, it can be regarded as speculative, but it's merely a picture to put in your mind. And this is, in principle, the vortex ring. You might think of it in those terms, with a sort of spiraling through the middle. And this is a cross section of a bit of that, looking like that. So it has a sucking pole and a spitting pole. Simple. Now, when you have a proton, you have a nice circuit of 3, and that's very good ether circuiting, holding them together very tightly, and so you've got a strong nuclear force. But if you only have 2 of them, it doesn't do that at all easily. It's much more easily disrupted, and that's what you see with mesons. When you have 3 quarks for a proton, there's stable, but adding another electron causes instability. That's because, again, you upset this beautiful circuit. And in fact, what happens is that when you have a neutron, the mass has gone up by more than 1 electron, nearly 2 electrons, although you think you've only added an electron. This means that some of the circuiting flow is now being diverted and making mass instead. Mutual attraction predominates statistically over repulsion because of the force gradient, and the force gradient is inherent in every force generating system. And any given position, infinitesimal convergence has more force effect at that same point than identical separation. That's why we only